problem 6.1-3. Find the maximum bending stress in the beam. We're given a simply supported beam with a distributed load, first uniform, then triangular, with an overhang at the end. And we're also given the beam cross-sectional shape with dimensions. We have everything we need to do this problem. The way we're going to approach this problem is to first draw a free body diagram and get the reaction forces. Then draw shear and bending moment diagrams. Once we have our bending moment diagram, we'll find our maximum internal moment. From there, we will use it in the Flexure formula to calculate maximum stress, and along the way we're going to need to get the moment of inertia for that cross-section. Summing the moments about point A in order to get the reaction force at this point I've called B. We have, first of all, this is the resultant force for the distributed load, 3 kips per feet times 12 feet, negative because of the direction, and its moment arm is 6 feet. Here is the resultant load for the triangular distributed load, 1/2 times 3 kips per feet times 6 feet, and its moment arm is 14 feet. That's 12 feet from A to B, plus 1/3 of the 6 feet is additional 2 feet for 14 feet. That's negative plus By times 12 feet. And solving for By, we get 28.5 kips. And summing forces in the y direction, we get Ay is equal to 16.5 kips. The next step is to draw our shear diagram. Okay, let's go ahead and draw the shear diagram for this beam. Right at the left end at point A, we're going to get an abrupt jump, Ay equal to 16.5 kips. Then from A to B, we're going to have we have a constant distributed load equal to a value of negative 3 kips per feet. So that means we're going to have a constant slope on our shear diagram, and it's 12 feet long. So we can calculate where we're going to end up. That'll be equal to 16.5 kips where we start, minus 3 kips per feet times 12 feet. We're going to end up at a negative 19.5 kips. Now when we get to point B, we see we have a jump of 28.5 kips. So we're going to get an abrupt jump right here at point B, or at 12 feet, over from the left end. We're going to jump from 19.5 up to a value of 9. And for the last remaining 6 feet, let's look at the area under our distributed load. It is a triangular shape, so with a height of 3 kips per feet. So 3 times kips per feet times 6 feet, that's 18 kips per feet, divided by 2 is 9. So that will take us from positive 9 back down to 0, and it's going to be parabolic in shape. Okay, it's going to look something like that. Now it's be useful to know right here where we cross the x-axis, and we can get that by taking this value 16.5 and dividing it by the slope of this line, which is 3 kips per feet, and that gives us a value of 5.5 feet. So that's right, that's this distance here to where we cross the x-axis. Okay, I've now drawn my axis for my moment diagram, and we can look at the shear diagram to get an idea of where we're going to go. First of all, because we have a pin support at the end, we know we start at a moment of 0. And because we have a linear shaped shear diagram, we're going to have a parabolic shaped moment diagram. And we're going to start out with initially a steep slope because we have a large positive shear, and when we get to a distance of 5.5 feet over, we're going to have a slope of 0. So it's going to be a parabola shape in between. The height of our parabola is going to be equal to the area under the shear diagram over the first 5.5 feet. Okay, it's going to look something like that. We'll call this area 1, and we can calculate it. We get for the area 45.375 kip feet. Okay, for x equals 5.5 feet up to 12 feet, we see that we are going to continue our parabola, and the distance we're going to travel on our moment diagram, or the change in our moment, is going to be equal to the area under this triangle I've shaded here. So the area of triangle 2 is calculated to be negative 63.375 kip feet. So we're going to drop up here from our 45.375 down 63.375, and we're going to end up at a negative 18 kip feet. So we get a moment diagram that looks something like this. And now for the final 6 feet of our moment diagram, we are going to we have a positive shear, which means our slope will be positive, and we expect to end at 0. And we can check to make sure that we've drawn our moment diagram correctly by calculating the area under this last remaining portion of our shear diagram. I've called that portion area 3, and it is what we call an exoparabolic shape. And it is equal to 1/3 times the base dimension, which is 6 feet, times the height dimension, which is 9 kips. That gives us a value of 18 kip feet, and that's exactly what we need to close this our moment diagram back to 0. What does the shape look like? Well, if this is a parabolic function here on our shear diagram, then this must be a cubic function. And we see that it starts with a steep positive slope, and by the time we get to the end of this beam, the end of the 6 feet, we have a slope that goes to 0. So it's going to look something like that. The next step is to read off the maximum moment on the beam, because we're going to use that maximum moment to find the maximum stress. And so we're looking for the largest value of moment, and that can be either positive or negative. In our case, it's positive. It's a positive 45.375 kip feet. Okay, the next thing we're going to do is calculate the moment of inertia for this cross section. And I'm going to show you a little trick. You remember back when we were calculating polar moment of inertia for a pipe, we could take the moment of inertia of the outer portion, the outer radius of the pipe, and subtract the moment of inertia for the inner portion. And we can do that for this rectangular tube-shaped beam. In other words, I can calculate the moment of inertia for this cross-section as the moment of inertia for the outside rectangle minus the moment of inertia of the inside rectangle. And I can do this because the outside rectangle and the inside rectangle both share the same neutral axis. If they did not, it would not be such a simple thing. I'd have to use the parallel axis theorem and calculate a value for d. So the moment of inertia for a rectangle is the base times the height cubed divided by 12. So let's go ahead and write that now. In the first term, we have the moment of inertia for the outside rectangle. It has a base dimension of 10 inches, a height of 12 inches. We cube it. That gives us units of inches to the 4th power. The inside rectangle has a base of 9 inches, a height of 11 inches, and we get a value for a moment of inertia of 441.75 inches to the 4th. Finally, we're ready to calculate the maximum stress. We're going to use this equation, which is maximum stress is equal to the moment times c divided by the moment of inertia. Okay, we plug in for m, our max moment, which is 45.375 kip feet. Because we want stress to come out in KSI, units of kips per square inch, we need to convert feet to inches. So we're going to multiply it by 12 inches per feet. That cancels out our feet. C is the distance from the neutral axis to the furthest spot away vertically on our cross section. And because our cross section is symmetrical about the neutral axis, so we can go either direction. So our value for C is going to be half the height, which is going to be 6 inches. And I is our moment of inertia, which we found previously, and we can calculate our maximum stress as 7.4 KSI. And we're done.